All right, let's start. So we're gonna begin with this example problem called people are leaving. So the statement goes, n people are standing in a line from positions 1 to n. You have to perform queries of two types. One is minus x, indicating that the person at position x leaves. And the other is question mark x, asking you to find the closest occupied position so that a person still stands there at y, which is greater or equal to x. So let's look at an example. Here n is 5, so there are 5 positions. Initially, everyone's in line. So minus 3, that means the third person leaves the line. And then question mark 3, so it's asking for the first occupied position that comes at or after 3. So in this case, it's 4. If the second person leaves, then the query at 2 would give 4 again. And if the fourth person leaves, then the query at 2 is going to give 5 instead. So from that, we have a very naive solution of just keeping track of a Boolean array of whether each position is occupied at any time. So for minus x, we just set occupied x to false. And to query, we just linearly scan through the array to find the first position x such that occupied x is true. And here's a slightly less naive solution. So we, instead of keeping track of whether each position is occupied, we keep track of the answer for each position. So R of I is going to be the answer for position I, or the first occupied position that's greater or equal to I. So if we have this array, then for queries, we can just print R of X. What about updates? So let's look at the example again. If the third person leaves, then the answer for position 3 becomes 4. And if the second person leaves, then the answer for the second position also becomes 4. So you might think that we can just do this. The answer for x after the person at position x leaves is the answer for x plus 1. But if the fourth person leaves right now, its answer gets updated to 5, which is correct, but the answers for positions 2 and 3 are not updated, and they remain the wrong number. So instead, for our query, we have to keep going to R of x until x is equal to R of x, which means that position is occupied. So even though this is slightly better, this solution is still O of n in the worst case. So we didn't really have any progress since our naive solution. But what you've just seen is a glance at DSU, which stands for Disjoint Set Union. So as its name suggests, it operates on disjoint sets. So basically sets that don't have elements in common. So for example, components of a graph. Every component is a set of distinct or disjoint nodes in the graph. Two components don't share a same node, otherwise that would be a single component. So if any of you have any questions, feel free to ask in chat at any time. And disjoint set union is also often called a union find data structure because of its two operations called union and find. So union merges the set that contains the element u and the set that contains the element v, and find u returns a representative of the set that contains u. So what is the representative of a set, you might ask? It's just something that uniquely identifies the set. And in this case, we choose a specific element of the set to represent the set because every set is disjoint. So a specific element of the set uniquely identifies the set. And if we have a representative for each set, then find u is equal to find v if and only if u and v are in the same set. And find u is not equal to find v if and only if they're not in the same set. Okay, let's look at some examples of this data structure. So if we have 1, 2, 3, 4, 5, each has their own set, then we have this diagram. And the arrows in these diagrams represent the representative for each element. So in this case, every element is its own set, so every element is its own representative. And here we have 1 and 2 as a set, and we chose 2 to be the representative for that set. So both 1 and 2 point to 2. And the same story goes for 3 and 5, where their representative is 5, and 4 is its own representative. Okay, so how would we implement union using this diagram? We can just redirect the arrows so that every set, the elements of every set point to the same representative. So if we have union 1, 2 here, then we can just choose one of them to be the representative. So here we chose 2, so we redirect the arrow from 1 to go to 2. And what if we want a union 2 and 3? Then we choose an element between 2 and 3 to be the new representative for the set. And here we choose 3. So now 2 and 3 have the same representative. That means they're now in the same set, but 1 still had 2 as its representative. So does that mean 1 and 2 are not in the same set? It shouldn't. So that's why when we implement find, we have to follow the arrows until the arrow points to itself. So if we call find 1, we'll go from 1 to 2 and then 2 to 3 and 3 back to 3. Then we know this is the true representative. This is the exact same thing as we implemented for the people are leaving problem. We have to keep following the R array to find the actual answer. So this is O of n, as I said before. And here's the naive implementation. So for find, while U is not the representative for U, we keep going to its representative. Then at the end, U will be the representative for the set where U is in. And for union, we first find the representatives for the 2 elements. And then if they're not the same, that means U and V were originally not in the same set, then we just set one of their representatives to the other. Okay, does everyone understand up to this point? Can I get some reactions in chat? Because I'm not sure if I can see any emoji reactions right now. Okay. All right, cool. Then let's see how we can make this better than O of n. Because right now, union is O of 1, but actually that was a lie. Find is O of n, so union might also be O of n right now. Actually, there's also this recursive naive implementation, which is more popular, I guess. So if U is equal to the representative of U, you just return U. Otherwise, you just call find on the representative of U. Okay. So here's our first optimization called union by rank, or in other words, the height of the tree. So here we're going to change our diagram a little bit. So before we had arrows from each element pointing to itself, representing that this is the representative element of the set. Now we're just going to omit those. So if there isn't an arrow, then there is an arrow pointing to itself. If that's not too confusing, but you'll see. So for union 1, 2, we choose an element to be the representative. So here we choose 2. But now note that we put 1 under 2 because we want to draw it as a tree. So we have a notion of rank, which is the height of the tree. So a node by itself has a height of 0, and if it has a node below it, then it's a height of 1. So if we want to union 2 and 3 right now, using the union by rank optimization, we want to choose the higher tree as the representative. So since the tree with representative 2 is higher than the tree with representative 3, we choose 2 to be the representative so that the height of the tree stays as low as possible. And if you do this optimization in choosing which representative to be the new representative, then it's going to be O of log n for find, which is also time complexity for union. And this log n comes from the max rank of any tree in your data structure. And to prove that it is O of log n, you can see that you need to union 2 trees with rank t minus 1 to get a tree with rank t. And if you do the math, you need 2 to the t minus 1 unions to get a tree with rank t. And you can only have n minus 1 unions if you have n nodes or elements. So the max rank is O of log n. I guess the important part is that the time complexity is O of log n. So that is way better than the O of n we had before. And here's the implementation. You see that the find operation is not changed, but for union, we check whether rank U is less than rank V, and we make sure that the rank of U is greater or equal to rank V. And then we set U to be the new representative because it has a higher rank. And then if they have the same rank, then our rank increases by 1. Okay, does everyone understand this part? Because I feel like this might be a little bit complicated. If you're all doing fine, then let's continue. So this is the union by rank implementation, and there's also a optimization called union by size, which is very similar. So instead of merging the lower rank tree to the higher rank tree, we merge the smaller size tree to the larger size tree. So it's basically the same, but instead of rank, we use size. And to update the size, we just add the size together. Yeah, and this is also O of log n, but it's easier to implement. And let's talk about a completely different optimization called path compression. So disregard all of the optimizations we just talked about, and suppose we got to this unfortunate chain of representatives, and we are calling find 1. Then it's gonna go down the chain and then propagate back, and it's gonna take O of n time, which we don't want. But we can redirect the arrows in this process so that subsequent calls to find is gonna take less time. So if we simply do this, we're gonna get O of log n too, without doing the union by rank or union by size. And the implementation is very simple. You just add this line. I hope you can see my mouse, but I'm going to do this. So every time you call find on your parent, I changed the representative to parent because we use the tree representation. But every time you call find on your parent, you update your own parent too, instead of just leaving the parent as is. And this will speed it up to O of log n. And if you actually use both union by size or union by rank with path compression, you're going to get O of alpha n queries, where alpha n is the inverse Ackermann function, which is just a synonym for a constant factor, because it's less than or equal to 4 for any reasonable n. And to solve people are leaving, which the example problem we started with DSU, in addition to keeping parent and size, we also keep the rightmost position of each node, which is the answer for that set. Maybe that'll be more clear in the code. So here in find, we have the path compression optimization, and in union, we have the union by size optimization. And in addition to size and parent, we keep an array called right, which is synonymous to the R array from before. And every time we union, we set right of the new set to be the larger value of the 2. So it always gives you the rightmost element in the set. Does this solution make sense? All right, cool. That's great. Then we can. Oh, actually, I guess there's this other slide. So if the X person leaves, then we combine the set that was at X and X plus 1. And then to answer the queries, we just output the right array at the representative. But yeah, okay, let's look at this problem. Go ahead and read it yourself, or you can look at this slide and think about it and see if you can use DSU anywhere. All right, anyone have any Thoughts? Well, if not, then let's just continue. If you look closely or think closely, you can see that all permutations, when you draw them as a graph, form disjoint cycles. And you can see that in this diagram. So 5 goes to 3, goes to 2, goes to 1, goes back to 5. So that's a cycle. And then 4 goes to itself. So that's also a cycle. And these cycles are disjoint. And it takes S days for each kid to get their book back, where S is the size of the cycle the kid is in. So the first kid is in this cycle that has a size of 4. So his book goes to 3, goes to 2, goes to 1, and comes back. So that takes 4 days. And the cycle the fourth kid is in has a size of 1. So he gets his book back the next day. So yeah. And then if P of I equals I, so if kid I gives his book to kid P of I, then they're in the same cycle. So with these observations, we can come up with a DSU solution. So for each I, we union I and PI. So because they're in the same cycle. And then the answer for each I is just the size of their set. So does that make sense to everyone?
I have a question.
Okay.
Is there a benefit to using DSU over, say, DFS to find cycles?
To find cycles. Well, if it's cycles in a general graph, I think DSU is the only way actually. But in this case, this is a very special graph where cycles are disjoint.
Yeah.
So you can just use DSU to union the edges, and you don't even need to check for direction.
Okay, but you're saying in the general graph, you would have to use DSU.
Well, I guess for directed cycles, yeah. But for undirected graphs, a cycle basically means an edge that unions 2 elements in the same set.
Okay.
Yeah, but that would only allow you to check if there's a cycle. But if you use DFS, then you can actually find the cycle. Well, I'm not seeing any questions in chat, so I will continue then. So here is another application of DSU, which is the minimum spanning tree problem. The spanning tree means a tree that contains all the nodes in a graph. And a minimum spanning tree is a spanning tree that has the minimum weight. So here in this graph, the red edges outline a spanning tree of this graph because it connects all the nodes together, and it's a tree. And this tree is the minimum spanning tree because it has the minimum weight out of all spanning trees. And Kruskal's algorithm is very simple to implement. One, to find the minimum spanning tree of any graph, and it goes like sort edges by weight, and then for each edge in that order, you connect them if they're not connected, and then that edge will be in the minimum spanning tree. And the time complexity of this is m log m to sort the edges, and then m times alpha of n to do the loop using DSU with both path compression and union by size. And here's a proof of correctness that's rigorous, but I guess intuitively, you always want to use the minimum edge to connect components together. And that is the intuition for this algorithm. Yeah. So here is a minimum spanning tree problem that literally just asks you to find the minimum spanning tree. So if you want to implement Kruskal's algorithm real quick, you can do that right now. All right, let's go. If you have any questions, comments, and concerns, please fill out our feedback form. And if you're on YouTube, make sure to like that subscribe button. Make sure to like the video, subscribe, and ring that bell, and leave a comment whether you like union by rank better or union by size better. And here's some practice problems and resources. And if you have trouble doing the first two practice problems, I got some hints here. So have fun.